Hi, everyone. My name is Matvei. I'm a machine learning engineer here at RoboFlow. And yeah, today we'll be talking about the state of object detection in VLMs and object detection models. And we will do it using RF100-VL, RoboFlow's most recent benchmark that we just released. And yeah, let's just get straight to it. We'll start off kind of with motivation here, like what kind of things are we going to be looking at and why do they matter? So we have this picture of an aquarium here with the fish. Say we want to detect the fish, and we want to see if Gemini 2.5 Pro can do that, because there were claims online that it does well for object detection. So basically, we can just ask it here to detect things. And as you can see here, it does pretty well, pretty close to like all the ground truth. I would even argue the red box is a little bit better, covered like the top fin. So you probably, but just based on that picture, could think that this is really good. And Gemini is indeed making some really good progress in object detection, but it's not as great all the time. So for example, if we look at the picture of this cable, the task here is to detect brakes. And so the way we do this actually is every time we want Gemini to detect something, we send it a prompt, right? Because it's a language model. It's not an object detection model. We prompt it. So in the case with fish, we asked it, hey, please detect all the fish. Here we ask it, hey, please detect all the brakes in the cable, or just all the brakes. In this case, the prompt is just detect all the brakes. It's a metal cable, has some tiers, and Gemini says that the whole cable is a brake, which I guess is not correct here, because yeah, the brakes are way smaller and way more nuanced. And this is kind of an example of it missing the general context of the prompt and just like the information that is required to perform additional kind of like understanding, visual understanding, and performing good object detection. So kind of inspired by that, we really wanted to push it further and evaluate in a lot of ways. Do VLMs actually reason visually and work with all this additional information like text, additional modality, and help it be more specific on tasks like that? Is there a way to make them be better and detect breaks if there's text for breaks? So that's kind of like the motivation for the work here. So yeah, basically here, the guess is that VLMs don't generalize as well outside of the pre-training distribution of theirs. So at some point, we suspect the Gemini was trained on some corpus of pairs of images and then text that corresponds to objects in those images, specifically like some sort of JSON format of objects in it. And if something goes outside of the distribution, this is most likely going to break. So this is just me. So once again, we'll just start kind of with a small little overview. Pre-trained VLMs, as we just talked about, pre-built for a range of different use cases. So it's every kind of VLM nowadays has a big pre-training run where it's training a bunch of internet scale data, where it sees a lot of images paired with text. It could be for different use cases, not just object detection. It could be visual question answering, some classification things. So a lot of things. And they're aimed at being generalist. So if you attended James's webinar, you would remember that actually is the post from his topic. So we're just kind of going to build up on that. And yeah, they're not very suitable to run in real time unless you have like a data center with a lot of GPUs. Then maybe you can do that. And so then on the other end of the spectrum, we have specific vision models that are designed for specific tasks. Like in our case, object detection, we have YOLOs, we have RF Data. And basically, yeah, they can run faster. They can narrow down a very specific task, but they lose this generalization ability. And they're way smaller, which is convenient. So in today's webinar, we're going to specifically be comparing the two on the task of object detection, which is the task that we all deeply care about, especially at RoboFlow. So let's get to it. And basically, yeah, like if you kind of follow the the description so far, it seems like there isn't really a reason to use a VLM for object detection. We're running a little bit ahead with this graph. We'll look at it at the end of the presentation, but I'm just showing it here for the trends. Basically, this displays different sort of figures or different architectures. So we have Qwen, which has 72 billion parameters, which is a huge vision language foundation model. And these are scores on RF100-VL, our latest dataset. We also have GroundingDINO, which is like a medium size, also VLM, but pre-trained specifically for object detection. Qwen was pre-trained for a bunch of vision tasks. And then we have YOLOs, which are just object detectors. And we can kind of see here actually a very counterintuitive trend that, as the model size decreases, the models get better significantly. So specifically in this case, Qwen is not fine-tuned. It's just a zero shad. And we'll talk about this triangle a bit later. And then GroundingDINO is at first zero shad and then fine-tuned. And then on a bunch of few shad examples, but we'll talk about this as well. But basically we can, and then YOLOs are a few shads, and then full fine-tune. But so what we can see here is that smaller models are faster, they are more accurate, they are more affordable and faster to train and to inference as well. And they can run on consumer-grade hardware. So basically, it seems like the answer everywhere is just to yes, use a small model that is focused on object detection because it's going to be so much better. This year is under 10 map. This year is 55, 60 map. So yeah, basically, why do we want to do that? And the answer is right now, first of all, we covered that briefly. VLMs, they have this generalization ability because of their pre-training. This removes a need for training in the future. So you can just run it out of the box, zero shot. And assuming that it was pre-trained well enough, it can detect objects right away, whichever one you care about. And you have flexibility of your natural language in this sense. You don't have to define a fixed vocabulary. You can just prompt it to find anything. So additional thing is, basically, if they can have a more rich pre-trained body, they can also cover more data distributions, which is important. We care about generalizing better outside of what we have seen. And we saw in the beginning example that it seems to be not the case for Gemini at the moment. And yeah, another really cool thing is that VLMs can use their generalizability to create more complex pipelines, just packed inside of one forward pass of the model. So basically, here we have this product that we call workflows. It's one of the RoboFlows products. Here we are combining an object detection model, stability AI in painting, SEM, and everything else is basically used to detect an object, and then swap it out with something else inside of an image. And you can see how there are so many different components. With a good VLM, supposedly, you should be able to just do it all as a single forward pass where you ask it hey, say we want to take a person and replace the person with a dog inside of some image. You can just ask a VLM to do it. So there is no more need to create a complex pipeline that creates all of those things. It's just going to be a VLM that takes an image and outputs whatever logic you gave it through the prompt. And then just looking into the future, right now, the running on the edge hardware is definitely a problem, but using a bunch of optimizations that are created for modern architectures like transformers and just modern hardware optimizations, like basically flash attention and all of those different things like quantization and things like that. The models should, in the future, be able to run on edge as the hardware and architectures both progress. And they should get close to real time eventually. So those would give us basically models that can kind of do everything beyond the edge. And that's a possibility of where the computer vision could be headed. So it is very important to be assessing the current state of those things. And that's why we're doing it here. So our claim here, the main claim, is that state-of-the-art VLMs should not currently be fine-tuned for specific tasks. But instead, as we said, we should leverage their pre-trained knowledge and see how it can be used, maybe by adding more modalities like text or basically like different images and stuff like that to basically motivate it to do better predictions. And specifically in this paper, we say that for object detection, whenever people annotate their data set, there is such thing as annotated instructions. So whenever you want somebody to annotate your data, you write instructions of what all of the things in your data set are and how to handle them. And we think that there is value in those instructions. So specifically, annotated instructions could be text about how to handle a specific object in the image, and then maybe image example of that object and how to better work with it. So this all seems like a very useful information that a VLM can work with because it knows how to read text. It knows how to combine text and images. So we wanted to study, does that actually help? This is kind of like the example of that here. Say we have this data set with a bunch of different garbage, metal, plastic, and a bunch of things like that. And so if you just ask it to find soft plastic, it's really hard in this like giant pile of junk. So if you give it some text that basically clarifies like soft plastic is transparent, semi-transparent, all of those additional things, it makes it easier. As well as maybe if you give it a few images of this plastic. So like if you give it a few examples, as in those images where it's present, we want the VLM to combine those two as an additional information to do an informed prediction, basically. And then same thing for metal here. Basically, you can see how you can use all of this additional data that you have as a annotator or like the owner of the data set to instruct your VLM to do better things. And that's kind of like this ability to work with more information and leverage your pre-training knowledge to just do better. It is what we want those VLMs to do. So we've previously done this project called RF100, which was this data set aimed at basically expanding the range of real world data sets applications where you can test how your model is working. And it was specifically aimed at like fine-tuning things on it that are specifically object detectors models. But those data sets were very different from Coco, which has limited images. For example, it doesn't have medical images. And so that basically kind of helps you understand how do your models actually scale outside of Coco into the real world. It had 200,000 images and no more. I had in 29 classes. But so now we have made a step further and we created RoboFlow 100-VL. And here VL stands for vision language, of course. And we kind of wanted to make it take it further with all of the data that I just described, like with all of the ideas in mind that I just described. So specifically, we have the 7 different categories of things. They kind of cover broadly a bunch of stuff, sports, industrial documents, flora and fauna. So medical images, aerial images. This time we have a little less images, 164,000, but we will get to that. They're a little bit more high quality here and convey more information. So yeah, let's basically go ahead and see what kind of stuff is there. So we kind of saw one of the tricky examples in the beginning, but there is more. There are a bunch of examples here where, once again, context is important. So block in the context of volleyball means somebody jumping and blocking the ball. If you ask a block in the image and the VLM does not know the notion of block in volleyball from its text pre-training, once again, it likely would fail. We've seen the wire example. So there's a bunch of scientific acronyms and concepts which really test the in-depth connection of those super specific things with super specific images. There's a bunch of things with a lot of categories where you need, as we saw, a lot of additional information, just like to be able to differentiate between all the things that you see. And then, there's a lot of multimodal imaging. Like we have infrared, we have this like wave signals, which is also very, very interesting and not a standard thing that VLMs or like I would suspect see during their pre-training. They might, but it's definitely like more rare. So it can have those edge cases as well. So yeah, that's the kind of like tricky things that we wanted to have there as like classes that you can use to prompt the VLM and make it see if it actually knows what it's talking about, combined with the images. Yeah, so we spent a lot of time, as you can see here, 1600 hours, 1693 hours labeling, reviewing, and preparing dataset. So we basically, yeah, filtered it with some heuristics in the beginning, just like to make sure it has some stars, had a lot of like valid number of annotations and things like that. And then we manually filtered them. That was like the longest part. We extensively like sat there and selected the best ones. So then we also made a version that has few shot examples. So that's specifically needed for things like providing few shot examples to the model, and then also just having a few shot version of the data set where you can fine tune on few shot and see how it does on the rest of the data set. So basically the two versions of the data set are available. There's a full all data and trunk splits, and there's few shot splits. And then what we did is we took those few shot examples with the objects in them. And an important detail here is that each we made sure the few shot examples include 10 instances of each object, but 10 instances of each class in the data set. And so we took those and gave it to ChatGPT and asked it to generate the annotated instructions for us to kind of speed it up for 100 data sets. And so that kind of gave us more information here to like more explicit text. And surprisingly, GPT knew like really a lot of them based on the images and just the class names. So that kind of shows that VLMs have this info somewhere inside of them. And then, yeah, we basically relabeled the data sets and double check the instructions. So a final step of cleaning the data set. And yeah, that's kind of where we arrived. That's RF100-VL. Please visit the page. It has the GitHub repo. It has our preprint version. And then it has all of the data in the universe, in the RoboFlow universe. So please do check it out. It's really easy to work with if you want to, yeah, get your hands dirty. So just a quick note on evaluating, just like how do you even do object detection with the VLM? It's not a very, there's not too much about it online. It's kind of like a new thing that's appearing. So like traditional object detectors, they are trained on a fixed set of objects and classes. So there is just like a number of objects in your data set, and you predict basically the bounding boxes, as well as the class label and then your confidence score about this prediction. And you know that your output is always going to be fixed with those networks because they have fixed output structure and dimension. But with VLMs, that's not the case at all because they are autoregressive. So they just basically generate tokens. And it just happens to be that during their pre-training, they saw a lot of images, after which they got a lot of tokens that look like specifically the shape of this bounding box predictions format. But yeah, basically because of their autoregressiveness and sampling, it does not guarantee that you will be able to always get the correct format. So whenever you do those predictions, you got to be careful. So for example, here we have this, like if you compare the box one and this like second bullet point, you would be able to see the kind of confidence is missing here. And then box that switched to box one. This is like real examples that I was seeing when we're trying to benchmark the VLMs on RF100-VL. Sometimes it's just like not consistent with this generation. So it's very important to do some sort of post-processing on those to actually get the valid predictions, or try to make it do some constraint generation or fine-tune it to output the specific shapes. But like the official guidance right now in the tutorials is to just do regular prompting. And so we've stuck with that for this work. And yeah, so just one final note on how currently the VLMs are being evaluated out in the field. This is from Qwen 2.5 VL paper. Here it is framed as a task of object grounding, not object detection, which is a significant difference. And we will get to that in a bit too. But basically, you can see those people riding motorbikes, and the prompt is to find basically motorcyclist and then wearing a helmet as a, or not wearing a helmet. That's like a predefined, they define that prompt to detect those two specific things. And so object grounding overall would be targeted towards finding a specific instances that relate to your prompt inside of the image. Versus an object detection, once again, you have your kind of like fixed vocabulary of all classes. And you want to find all of those classes, like regardless if your prompt is specifically for one or for the other, you want to be always detecting all of the classes together. So it's like find everything that you know versus find the specific thing. And this makes quite a bit of a difference when we try to evaluate things. So it's important to know the distinction. But yeah, in this picture over here, you can also see the kind of like output the Qwen provides. So it's like, once again, bounding boxes, labels, and you can make it to sublabel. And so yeah, basically the cool part about those VLMs, once again, is that you can give them natural language of what you want them to do. And here we can kind of like add additional thing like not wearing a helmet, for example. So basically just a little bit more on evaluating object detection versus visual grounding. So say we have this Clash Royale thing, and we want to just detect characters in it. So what kind of like Qwen's way of evaluating it would do for visual grounding, and that's, we can test it too. The prompt would be something like, this is actually a prompt for Gemini, but it's like a Qwen's format of evaluating it. We will ask something like detect all 2D bounding boxes of class name. So class name would just be whatever class name you're looking for. And the key thing, this is what the Qwen paper does here, where it reports the results on W and all of the other tasks, is it would go ahead and use each class individually and do a separate inference call for that class. So it would take a class LI bottle, and it would run the prompt detect all 2D bounding boxes of LI battle RAM, whatever that is. And so it would run, for each image, is going to run n inference requests, where n is the number of classes in your data set. And then it's going to combine all of those predictions, as you can see in this image. And that's your final predictions, which is not how originally object detection is done. Because yes, as we've mentioned, we want to detect all objects at once. And you can see it here. You can see that like there's 6 or 7 different bounding boxes on that tower. And so then when you're calculating the metrics, it is very important also to, basically figure out what do you want to calculate the metrics over, because from our understanding, the Qwen paper only calculates its metrics by taking the detections whose class is one of the classes that are present in ground truth data. So say that enemy bot was not present in ground truth data, but it predicted the enemy bot, it will not be using the prediction for calculation of map, which is once again not very helpful for understanding how good the model is and actually detecting the right things. So basically, like this, if one of those boxes is correct on this guy, is going to be used towards calculating the good positive map, and the rest of the boxes would just be discarded because they're not in the ground truth, and that's pretty misleading. So, kind of the way that we propose to do it, and do it in our paper, is we ask it to detect, just like in regular object detectors, all of the 2D bounding boxes of all of the objects. So we just say detect 2D bounding boxes of all of the following objects, list of all categories, so every object is present, and compute map basically with all of them. So yeah, that's That's it. Here, it only detected 2 things because there was so much more things to detect. And it just did 2 enemy executioners. So pretty different performance actually between those 2. And also here it ran n prompts. So it ran the inference n times versus here just ran the inference 1 time. So this is more efficient. It only runs 1 inference request, which is once again more similar to real-time object detection. And yeah, you can see that the results of detections are very different. And just so you know, for all of the further numbers you'll see in this presentation, that they are computed in this way on the right. Okay, so just a quick kind of like overview of the ways we wanted to include more information for, this is all for Gemini. All of the prompts here are for Gemini 2.5 Pro. And we wanted to see if we can get it to take in more information and use that for better prediction. So here, first of all, you can always specify the system prompt. So we just say return bounding boxes as return array with labels, never return mask or code fencing. So just for easier parsing afterwards. Our default base prompt is detect the bounding boxes of the following objects. And then we have class names. And then that's where our kind of like additional information comes in. We evaluate just like this mode, but then we also evaluate it by saying, so we give it the regular prompt, and then we also append this part saying, use the following annotated instructions to improve detection accuracy. And we will give it the annotated instructions that were generated by ChatGPT for this data set. So specifically, this data that ChatGPT generated for us during the steps that I was explaining. So we kind of rely on Gemini having enough sort of processing capability and just like reasoning over all of its tokens to understand that these instructions are describing objects that you might be interested in detecting, and they might have useful information about those objects and hopefully help improve the detection. And then same thing is few shot examples. We actually do it in a way that we kind of pre-create the conversation with Gemini, because we've seen a lot of resources that say that it is better to do it this way. They're pre-trained in this way. Basically, we like take each example. So we take an image from our few shot splits, and we kind of in our message to Gemini, we include it as like a turn where a user sent a message saying like, hey, detect objects in this image. And this is the image from few shot splits. So we know the ground truth of that image. And then we simulate that the Gemini sent a response. And that response being the ground truth actual bounding boxes of that image. So we basically like take the image and then say Gemini responded with this. And we give it to and we stack those together in a list. And then at the end of this list, we just say, hey, now detect bounding boxes in this image. And we give it the actual image we want to detect stuff on. So it kind of almost goes through its history that was artificially created for it with our ground truth data. And it kind of, it's supposed to see through all of those examples and be like, okay, if those were this, then I should probably detect this one here as well. That's the idea. And yeah, so that's basically the setup here. And one final thing on prompting before we go to our results and findings is the structures of the prompts really do matter. We found that simply changing a prompt from what it was in a default like Gemini tutorial kind of here, it was more verbose and it specified the specific format it should return. Y minimum, X minimum, Y max, X max. And then I was saying normalize between 0 and 1,000. Once we switched it, just by like playing around to this simple prompt, the one that we had in all of our examples, we got a +2 map over the whole RF100-VL for Gemini 2.5 Pro, which was very unexpected. We speculated this was because it's just simpler and Gemini already has all of this format kind of in its pre-training. Like if it was pre-trained specifically on examples that are structured in this way, it already has those embedded in its weights and just its knowledge. So maybe a more concise prompt can lead to better detections. So this was a very interesting finding. that you can just get way better results to map is very, very huge with just changing the prompt. So there's definitely a lot of work that could be done on top of that if you're curious about playing around with VLMs and their like object detection capabilities. But yeah, so we are now at the results. There's a lot of things in this table because we evaluated quite a lot of models. But I think we should first focus just like on Qwen 2.5 VL and Gemini. So we will first focus on this zero shot, first row zero shot part. So the class names only row basically means our regular prompt that we saw. And then where we just ask it to detect all of the objects. So for Qwen, we only got the map of 5.4. And for Gemini, we got map of 13.3, which is very impressive. And yeah, super cool. Not super high. 13.3 is not a crazy map, but which basically just shows that those datasets are hard for models to figure out. So then we evaluated the next one as by providing it additional instructions. So we just took our original prompt and then also gave it the annotated instructions of the dataset that were generated by ChatGPT. And as you can see here, Qwen was able to use those to improve. It got 7.4 instead of 5.4. But Gemini, very surprisingly, actually got 6.1. So it like dropped by more than a half. And if you kind of follow that trend here, down in that table, there's on the bottom, there's more Gemini, the bottom two rows. We gave it same thing with just images and instructions plus images. So images is our few shot examples scenario that I outlined. And then instructions plus images are just two combined. And we also observed that Gemini did not improve, but rather lost in performance. And for Qwen, the result kind of stayed the same for those, for images plus instructions, as the previous one, it improved by a little bit. So specifically for Gemini, we are attributing this very interesting result, which is like very counterintuitive to what we were expecting it would do. We were expecting it was capable to reason with illustrational data and include it for better detection. But instead, it got worse. So what we suspected is during its pre-training, it saw very specific scenarios, very specific format of object detection, image to text pairs. And once something that we provided to it got out of that distribution of things that it saw, for example, we've expanded our window quite a lot, the context window. We gave it a huge data set. We gave it a lot of few shot examples, and that's not optimal at all. It definitely costs, or it seems like here, definitely cost the model to just get out of its distribution and just kind of do whatever. So we view this as an evidence that at least Gemini is not able to truly use this additional information to its benefit, to get outside of its training distribution, basically, and go beyond. Like it could not actually use all this data. Seems more like a pattern memorizing here, in terms of it might have seen a lot of data that was object detection related, but it did not learn to, properly get outside of that distribution. With Qwen, it's a little bit better. We see the whole two map increase. And then here it also increases by 0.1. But I should mention that with Qwen, for few shot examples with images, we were limited by its API. For 72B, we used the API, and we were only able to include 3 images as few shot examples. So it's possible that it could have gotten better with more images as well. But then overall, the scores for Qwen are way worse than the scores for Gemini. So it's kind of like the two different problems here. One is just like really low and maybe displays some signs of being able to adopt traditional context, versus Gemini just seems to not be using it, but also seems to be like a very capable model. So it does get the highest score of like large scale VLM here, 13.3. Yeah, so that's kind of our main finding with the VLMs. Very surprising, but also promising since a lot of work could be done here. Additional really interesting thing here, we don't have to like talk about all the models, is GroundingDINO. GroundingDINO is just another VLM, but it was specifically pre-trained on object detection, just open vocabulary object detection. So you can also specify classes that you want as a natural text prompt here, and it can do open vocabulary detection. So zero shot is 15.7, and then fine tune it's 33.3, which is the highest few shot fine tune. So all of the fine tunes here are few shot. So we only fine tune the 10 shots, meaning 10 instances of each class for this fine tuning for each data set. So really not a crazy amount of data. And if we compare it with YOLOs, we really do see that GroundingDINO has way higher score at the result at the end. I think like 23.4 is the highest one for YOLOs versus 33.3 for GroundingDINO. And we view this as a pretty good signal that more like foundation model with a lot of pre-training and knowledge do seem to benefit a lot when serving as a backbone for fine-tuning something on additional data sets, or just grounding something for object detection. All of this learned information from larger pre-train is definitely useful. But then also GroundingDINO is just way larger model. So that also should be accounted for. Okay, so we're good here. This is just another additional part of our results. We did semi-supervised and fully supervised trains with YOLOs, just kind of like to see how far can we get on the data set. And then LW there as well. And yeah, we can see that the highest score here is 59.4. So that's kind of a good sign here that the data set is not too simple, even with the full fine tune, with all of the available train data. The maximum we're able to get to with LW data medium is 59.4. So there is a lot of room for improvement, even with fine tuning, and a ton of room for improvement with zero shot VLMs prompting. And that's where we really want to see the community do more work on it. And so, yeah, we're kind of back to that graph here. I think with the most important takes from this sort of like experiments here. So yeah, basically state of the art VLMs struggle a lot, and it highlights where they could be improved, specifically in being able to use the multimodal data that is available to it, like the instructions, and just being able to generalize to out of distribution objects by using those, and just also not memorizing the patterns as much. So that is a very feasible and good place to improve. And then small fine-tuned specialized models are still the way to go for object detection. So I think in most cases where people currently need like just like an object detector, the answer is always just a small specialized model. And then the large pre-trained backbones are helpful as a backbone for novel architectures in object detection, which is our GroundingDINO case here. We can see basically on those squares the GroundingDINO L few shot examples fine-tune significantly outperforms the YOLO ones, but it also is significantly larger, as mentioned. So this is kind of our takes here. I think one last thing I would like to show as kind of like a sign of hope is we measured Gemini Flash 2.0, Gemini Flash 2.5, and then Gemini Pro 2.5. And you can see that these models were created before our dataset was created. So they kind of independently are improving on it, which is great. It seems like the Gemini is doing work in the direction of the open vocabulary tasks in the wild. But yeah, we still think that there is a lot of space to improve. and the numbers show that as well. But it is interesting to see that they were improving independently of that and getting better, but also the models were just getting better and everything as well. So it's great to see that object detection is also getting better. So, okay. Now I have just like kind of this final announcement. If what I was talking about here seemed interesting to you, we currently have a challenge going on. It's called RoboFlow 20 VL, Few Shot Object Detection Challenge. RoboFlow 20 is directly a subset of RoboFlow 100 VL. And this is specifically, once again, a few shot subset. Here, there's a link for eval AI server. I will send it in the Zoom chat as well. Or yeah, basically you can find it with this link. Basically, yeah, the challenge is just to train the best model that can handle this data set. We have cash prizes for the winners. And the best teams are going to be mentioned at the CVPR workshop on visual perception and learning open world in another world. So yeah, please do participate if you are interested. It ends on June 8th. Good luck. And yeah, I think this is it for me. I will open it for the questions. And for those on YouTube, please subscribe, come to webinars in person, and we will be super happy to see you here.